Hey everyone, welcome back to the lab. I'm Dr. Chem, and today's explainer is an exclusive, highly detailed briefing on what I honestly consider an analytical masterpiece, the spectroscopic estimation of trace nickel in cooking oil. If you're someone who appreciates the absolute elegance of a perfectly executed chemical extraction, paired with the rigorous certainty of spectrophotometric analysis, well, you are exactly in the right place. We're going to be breaking down a brilliant methodology for quantifying toxic trace metals in edible oils, and we're drawing our data straight from some groundbreaking research in analytical food chemistry. So grab your lab notebooks because we are about to do some serious, high-level molecular detective work.
Okay, let's just dive right into the fundamental problem here. How exactly do we find a trace toxic metal that is hiding out in a thick, chaotic sea of lipids? I mean, think about it. Edible oils, whether it's your premium olive oil, sunflower oil, or just everyday soybean oil, they are incredibly dense, highly complex, and viscous organic matrices. Trying to isolate a single microscopic trace element from them is, well, traditionally, it's an absolute nightmare for analytical chemists. It's definitely not like working with a simple water sample. You have to somehow isolate and pull out that target metal without completely destroying the entire sample matrix, or worse, accidentally losing your analyte along the way.
Precision is paramount here, so here's our agenda for today's explainer. We'll start with the hidden nickel problem, introduce the MSE molecular key, walk through the UV-Vis spectroscopy protocol, cover the FAS extraction method, and then finish up by validating our results. Let's get to it. Section 1. The hidden nickel problem. Let's establish the scene of the crime. So nickel isn't just some minor nuisance that degrades nutrients and ruins the shelf life of your cooking oil. It is a serious, quantifiable biological hazard. Trace nickel can actually sneak into our oils from a bunch of places: the soil the crops grew in, agricultural fertilizers, or even the heavy industrial machinery used during the pressing and production process. And once it's in the oil, it doesn't just sit there quietly. It aggressively catalyzes oxidation reactions. This forms toxic downstream compounds like aldehydes, ketones, and peroxides, which leads directly to discoloration and rancidity. And because it's a trace element, you can't smell or taste the nickel itself until that catastrophic chain reaction of oxidation has already ruined the whole batch. But more importantly, exposure poses severe health risks, including eczema, allergic contact dermatitis, and even potential carcinogenic effects. So absolutely precise quantification is crucial for food safety. And this slide right here brilliantly illustrates our methodological evolution. We are finally ditching the slow, dangerous acid digestions of the past. Historically, chemists had to use open-vessel wet digestion or dry ashing. They were literally burning the oil in a furnace or boiling it in concentrated, highly corrosive acids just to break down the lipids and free the metal. Honestly, it was a total nightmare. Those old methods are agonizingly slow, sometimes taking an entire day. Plus, they're acutely hazardous to the operator, incredibly expensive, and super prone to analyte loss or external contamination. Instead, we're looking at a novel complexation method. This allows for direct sample introduction using specialized chelating agents. It's elegant, rapid, and it's an entirely non-destructive chemical solution. A real game changer. All right, section 2, the MSE molecular key. Let's meet our chemical savior. Enter MSE, or, for the chemical purists in the audience, N-N-bis for methoxysalicylidene ethylene diamine. Yeah, that is quite the mouthful. Basically, this molecule is a tetradentate Schiff base. You can think of it like a perfectly engineered molecular claw. It's a highly specific chelating agent meticulously designed by chemists to hunt down and complex tightly with nickel ions directly inside a highly viscous oily medium. It completely ignores the lipids. It literally only cares about the nickel. Now check out the exact chemical structure of this ligand. Notice how the Schiff base features these critical nitrogen and oxygen donor atoms. These atoms act as the precise teeth of our molecular claw, and they're sterically spaced to perfectly fit the specific atomic radius of the nickel lock. When this ligand bumps into a free nickel ion floating around in the oil matrix, it immediately wraps around it. It shares electron density to form a highly stable, uniquely yellowish-green one-to-one complex. It basically plucks the needle right out of the haystack. So the really crucial point here is this specific number, 6540. This is the molar absorptivity coefficient of our newly formed complex, measured in liters per mole per centimeter. To put that into perspective, once our MSC binds to the nickel, it generates a massive, vibrant, and easily measurable absorbance signal. Now, the analytical researchers deliberately chose to measure this absorbance at the 396 nanometer wavelength.
Why that exact spot on the spectrum? Well, the complex actually peaks a bit higher at 327 nanometers, but the uncomplexed, leftover, free MSC ligand heavily interferes at that lower wavelength. But shift up to 396 nanometers, and the free nickel and the unbound ligand become essentially invisible, giving us a pristine, completely interference-free reading of just our successfully captured target. It's an absolutely brilliant exploitation of spectrophotometric principles.
Section 3. Protocol UV-Vis Spectrophotometry. Let's walk through the rapid analysis.
Let's see how this precise chemistry actually translates into a rapid, highly repeatable lab procedure. First up, we precisely weigh exactly 2.0 grams of our oil sample on an analytical balance. Dilution requires a highly specific mixture of N-hexane and acetone at an exact 1:4 ratio. Why this exact blend, you ask? Because it completely overcomes the natural turbidity and thickness of the complex lipid matrix. It actively strips away the cloudiness to yield a perfectly clear, transparent solution for optics. We then add our MSC chelating agent and a standard nickel addition. And here is where the magic happens. We wait a mere 20 seconds for the complexation to occur. Just 20 seconds. Finally, we measure the absorbance at our chosen 396 nanometers against a reagent blank. I mean, just behold this kinetic data. This curve is honestly perhaps the most impressive part of the entire explainer. Remember, in older traditional methods, sample prep and digestion could take a grueling 12 to 24 hours. This kinetic plot mathematically proves that the MSC ligand hunts down, binds the nickel, and reaches complete thermodynamic equilibrium in a blistering 20 seconds. Plus, observe how the curve flattens out. It remains completely stable for at least 25 minutes afterward. This gives the laboratory analysts plenty of time to transfer their cuvettes and take their spectrophotometric readings without any panic about the signal degrading or shifting. Moving right along, Section 4, Protocol Fast Extraction Method. Now, what if we need to physically separate the nickel entirely? Say, moving it out of the organic lipid phase and into an aqueous phase for a completely different type of instrument, like flame atomic absorption spectrometry, or FAAS. For that, we use a slightly different liquid-liquid extraction protocol. And to find the absolute perfect extraction conditions, the researchers didn't just guess or rely on outdated literature. No, they employed central composite design. Instead of changing one variable at a time, which takes ages and completely misses the compounding effects between variables, this sophisticated statistical modeling technique optimizes everything simultaneously. The absolute peak extraction efficiency occurs exactly at an MSC solution to oil mass ratio of 0.97 milliliters per gram, a continuous mechanical stirring time of precisely 15.4 minutes, and an environmentally controlled extraction temperature of 29.7 degrees Celsius. These 3D response surface plots visually map out our optimized parameters, and they are basically chemical treasure maps. They beautifully demonstrate how these three variables, ratio, time, and temperature, interact and influence one another dynamically. Notice how the peaks in the visual map represent the mathematical certainty of the maximum recovery rate. You can see exactly where the chemical landscape hits its absolute zenith, ensuring the highest possible extraction of trace nickel from that stubborn oil matrix. It's a masterclass in eliminating trial and error in analytical chemistry through advanced statistics. Finally, Section 5. Validating the results. Let's look at the hard stats. A brilliant methodology is nothing without ironclad statistical proof, right? The theory is undeniably sound, but does it actually hold up under extreme analytical scrutiny? Well, look at these rigorous analytical parameters. By running 10 independent blank solutions, the researchers confidently calculated a limit of detection of just 0.24 micrograms per gram and a limit of quantification of exactly 0.82 micrograms per gram. What does that actually mean in practice? It means our instrument can reliably spot and confidently quantify toxic nickel down to minute fractions of a part per million. That is incredibly precise. The relative standard deviation across multiple runs is a very tight, highly reproducible 3.8%. And when officially tested against a certified oil-based organometallic standard, the FAS method yielded a remarkable 93.8% standard recovery rate. But what happens when we move out of the idealized standard solutions and into real-world, messy samples? The analytical team actually took commercially available soybean, sunflower, and olive oil straight from the grocery store shelf. They spiked them with tightly controlled known quantities of nickel and ran the rapid UV-Vis complexation protocol. And the technique holds up beautifully, completely regardless of the specific lipid matrix interfering. We're officially seeing a 104% recovery in soybean oil, 97% in sunflower oil, and 96% in olive oil. The targeted complexation method punches straight through those natural matrix interferences like they aren't even there. And a student t-test mathematically seals the deal on this research.
When comparing the instrument's calculated values directly against the known manually spiked amounts, the experimental t-values generated were sitting well below the critical statistical threshold. This definitively confirms that these rapid, non-destructive extraction methodologies are just as incredibly accurate and reliable as the agonizingly slow, hazardous, traditional digestions of the past. This isn't just a close estimate, folks. It is statistically indistinguishable from absolute perfection at a 95% confidence interval. We've seen how elegant applied chemistry and precise statistical optimization can solve massive analytical headaches. I mean, turning literally hours of dangerous boiling acid prep work into a blistering 20-second room temperature complexation is just wild. So, if our molecular detective work can expose toxic trace nickel in mere seconds using exactly the right ligand, it really leaves you wondering, what other trace elements and invisible heavy metal contaminants are lurking inside our pantry right now, just waiting for the right molecular key to bring them out of the shadows? Thank you so much for joining me in the lab for this deep dive explainer. Keep asking those hard questions, and I'll see you next time.